Good morning. My name is Janie Montblanc, and on behalf of the Great Basin Fire Science Delivery team and partners, I would like to welcome you to our webinar, Using Weather Data and Adaptive Management to Improve the Probabilities of Successful Revegetation, presented by Stuart Hardegree with the USDA Agricultural Research Service Northwest Watershed Research Center. Before I introduce our speaker, I want to let you know that you may ask questions at any time during this webinar by typing them into the questions pane of your control panel at the top right of your screen. I will field questions for Stuart after the presentation, but if you have technical questions for me, I can respond at any time. I will show up as the Wildland Fire Lessons Learned Center in your questions pane. Also, if you want to test your audio from your control panel, you may do so at any time and it will not affect the webinar. Now I would like to introduce our presenter. Dr. Stuart Hardegree is a plant physiologist with the USDA Agricultural Research Service Northwest Watershed Research Center in Boise, Idaho. His research includes physiological ecology of rangeland species, plant and soil water relations, plant establishment, and rehabilitation of disturbed lands. He is currently developing a database of rangeland weather and seeding information to aid in adaptive management planning by public and private land managers. Welcome, Stuart, and thank you for being here today.
Thank you, and welcome to the webinar. I'm going to be talking about using weather data to facilitate planning and management for rangeland restoration applications. ARS has a regional rangeland restoration research and management program called the EBIPM program. I'll be referring to that. EBIPM program is focused on technology transfer and has produced a number of guidebooks, and all these things can be downloaded from their website, which is showing on the screen. I'm mostly going to be talking about one of these guidebooks that I helped develop that you can refer to later that'll include a lot of this information. A large number of other collaborators, however, that have contributed to this or supported what I'll be talking about today. I'd like to acknowledge them on this screen. In particular, thank Janie and the Great Basin Science Delivery Project for facilitating the webinar, and the Great Basin Research and Management Partnership, which is sponsoring this particular series of webinars. The Great Basin Research and Management Partnership is a regional collaborative group that anyone can join by clicking on this link. Their focus is on facilitating solving regional issues through collaboration, through science and management. I listed all the mission goals here, but I especially want to talk about collaboration today. And as part of this seminar series, we want people to explicitly mention collaboration and what opportunities there might be to work with other people. In this era of limited resources, leveraging those resources is very important. I'll mostly be talking today about rangeland restoration options, and particularly those that are weather dependent. This is a schematic of what we commonly see in much of the Great Basin sagebrush bunchgrass rangelands that have been invaded by introduced annual weeds, which increases the fire frequency, and after burning one or two times can exhibit annual weed dominance. All of these transitions between these different potential phases are weather mediated. Historically, if some of these invasive weeds weren't around, there would be natural recovery following normal successional processes. These days, with weeds present and increased fire frequencies, and given the drought conditions on most rangelands that favor these introduced annual weeds, you can get locked in a fire cycle that just goes between bare ground and dominance by weeds. If we're trying to manage this system and change the trajectory and get back to some kind of functional or native plant diversity, We have to take advantage of the fact that weather is driving restoration success in many of these systems, and there might be things that are possible in a wet year. There might be other options through things like assisted succession that might be feasible in a dry or moderate year, but fairly frequently there'll be years when it doesn't really matter what you did, or whatever you do may only be partially successful. I'm also going to be referring to the general structure we use in the BIPM program to think about restoration planning and management. Most people doing restoration these days use a successional framework that recognizes that these systems are dynamic, recognizes that a given place that needs restoration has unique properties of the system that are going to affect the potential for restoration success, and that we actually know enough now about ecological principles that we can base our planning strategy on those principles, address directly the processes affecting vegetation change, and pick tools and strategies that may be limited to what we have available, but at least are related back to these ecological principles. So in these highly diverse systems, we can plan and understand within the context of the high variability we have in these systems. And today I'll be talking mostly about the weather variability aspect. The first thing I did when I gave a similar presentation before was survey this schematic and see which aspects of it were affected by weather variability, and it's pretty much everything, and having a diagram like this isn't very useful. Fortunately today, though, I have a little bit more time. I usually have to pick one of these circles and talk about that in a 10 or 15 minute time frame. Today I'm going to be able to talk about two aspects of weather effects on successional restoration framework. One is the importance of weather and how weather interacts with our management, and things that we can do to optimize microclimate for establishment of desirable plants. And I'll then talk about how weather variability and information can be used in planning and interpretation of results and as a basis for adaptive management. First, I'll give a few definitions. Most people generally understand what weather is. Weather is what happens. It's the atmospheric inputs that drive a lot of these system processes. I'll also define and talk about a couple of related processes and terms, climate and microclimate. These are often misunderstood, but they have some fundamental ramifications when you have to talk about using weather-related information for establishment success. Historically, weather information as in atmospheric inputs has only been used in rangeland restoration for retrospective analysis. We live on rangelands that are relatively dry and highly variable, and so the principal use of weather information is to rationalize failure, because that happens a lot. And it's often a justified rationalization because rangelands are characterized by episodic drought and high variability. The reverse isn't true. If we have success, we usually attribute success to other factors. This is what often happens. But what I'm going to do today is talk about how weather information can be used to improve restoration success, or at least optimize what we're working with. Climate has a little bit different definition. Often we use weather and climate interchangeably, but climate is a long-term average of weather. It's the type of thing we use when we're trying to pick suitable plant materials. It's long been observed that plants and vegetation communities have distinct patterns over space, and those are related to long-term climatological variables of water availability, temperature relations. We often use maps like this and tools of this kind to pick appropriate plant materials, either plant materials that existed in a given area historically, or picking introduced plant materials that we think might be useful for restoration at a given site. There are a whole bunch of rangeland planting guides out there. They all have this type of information in them, description of plants and their suitability for different climatic regimes. There's generally a table or a figure in there showing you diagrammatically how different plant species might be suitable to different precipitation regimes or effective precipitation, which might be viewed as precipitation in concert with soil conditions that affect available water. Unfortunately, the microclimatic conditions, the year-to-year conditions in the seedbed where a seed or seedling is trying to develop, they're much more restrictive than the long-term climatological controls on mature plant community distribution. So what I'm going to talk about first today is how weather interacts with the soil to affect microclimate and how we might select management techniques to optimize microclimate. Microclimate is what the seed or seedling or adult plant sees. It consists of the soil and near surface where plants are interacting directly with the atmosphere. One of the principal things that affect microclimate is soil type. Soils can have different textures and different layers that affect water availability. And these soils are highly variable over space. That's something to always consider when planning restoration in larger disturbances. You can have high variability in soil types over space, and each of those soil types is going to affect microclimate differently. Microclimate is greatly affected by other plants, and in our area and what we're talking about today, invasive annual weeds have a huge effect on microclimate. This is a fairly dense patch in Medusa Head. From one of our experimental sites, this is a picture of cheatgrass water use over 4 different years. In one of our field sites, this represents volumetric water content under cheatgrass, which are the dark circles, and bare ground, which are the open circles. Things like cheatgrass can move into a system. They've evolved to opportunistically use resources more quickly than the native plants that might be in the seed bank. And if things get tough or things dry out, they just set seed and die. That's their whole syndrome. It's a very, very tough competitive situation when you have large-scale disturbance, and these annual weeds that are geared towards reproducing every year or competing with some of these longer-lived species that aren't used to doing that every year. Usually when we're trying to establish what we want, we use controlled disturbance to improve the microclimate of the seeds or seedlings that we're planting. We use a variety of tools to modify the soil and improve microclimate. Some of them work better than others in different environments. Mostly we try to use controlled disturbance to improve the likelihood that a seed will end up in a favorable microsite. When we modify the seed bed, we can affect resource capture by creating microtopography, perhaps change infiltration patterns that will facilitate survival and establishment of seeds and seedlings. One of the principal things we do with seedbed treatments is firming. After sequestration, this picture on the right is all we could afford now for firming the seedbed, but firming does a number of things. It improves seed-soil contact. It's very important for water uptake and the ability to hydrate when water is available. It improves water distribution to the seeds by increasing hydraulic conductivity. Firming also reduces the surface area for evaporation. The less surface area there is, the less the conduit there is for water loss from the seed bed. In a lot of cases, but particularly with small seeds that have to be seeded near the surface, soil firming can actually press them into the surface, leaving them at the surface where they need to be, but still improving hydraulic contact. Microclimatic effects of controlled disturbance are mostly related to, well, they're depth dependent. So they're mostly related to placing the seed at an appropriate depth relative to the surface and relative to the disturbance. There's always a trade-off between energy for emergence and water availability. If you're near the surface, you're subject to the kind of variability you see in the atmosphere. The lower you are below the surface, the more that's moderated, and the greater likelihood you'll have a more favorable thermal and water environment. The problem is the deeper you're planted, the more energy it takes to get to the surface to put out your leaves and photosynthesize. Most of those seeding guides that I showed in an earlier slide give guidance on appropriate depth of seeds. It's usually related to the size of the seeds, but some species have other factors. A lot of times plants are adapted to be near the surface. Usually those are plants that produce few seeds. Those seeds might need to be near the surface, and they might actually sense light, and if they can't sense the light, they don't bother germinating because they wouldn't be able to emerge. It's relatively difficult to control seed placement, so one microclimatic strategy with controlled disturbance is to plant more seeds to increase the likelihood that you will have seeds in the optimal safe site. In general, most seeds, except small ones that have to be near the surface, do better when they're covered because it improves water availability and reduces thermal stress. The literature is somewhat biased because you only see literature that includes some success, so you don't see a lot of literature from really dry years, but drilling or seed placement generally improves success over broadcasting, which we often have to do in complex terrain or if we don't have drilling equipment or if the surface is too rough. A disturbance can also have direct effects on weed competition. After fire in a cheatgrass area, cheatgrass seed loads could be dramatically reduced. There's some examples in the literature of fire reducing seed densities from 15 to 20,000 per square meter to less than 1,000 per square meter. Unfortunately, mostly when we plant desirable seeds, it's less than 1,000 per square meter, so we still have lots of weeds to deal with. Mechanical disturbance can have different kinds of effects on weed germination and establishment. Disturbance can stimulate weed germination if it moves them to favorable microsites or releases nutrients that they can take advantage of, but controlled disturbance can also be used to bury weed seeds before seeding desirable species. The surface is where a lot of things are happening and where things are highly variable. Covering the surface with mulch can be very beneficial. It moderates temperature, it will reduce erosion, but it's relatively expensive and only used in areas where erosion control is the principal goal, or in highly disturbed areas like mines or mine reclamation. The thing about microclimate is what the seedling sees, but when you use seedbed preparation to modify microclimate, you're really only optimizing what the weather is allowing you to work with. Seedbed treatments are prescriptive in that if you use them every year, they're going to have a different effect because weather interacts so strongly with temperature and water availability. I'm going to go back to talking about weather now. As we said before, weather is what happens. It's the real-time expression of these atmospheric variables that affect temperature and water. For the rest of the talk, I'm going to talk about how weather information can be used for planning and improving planning, improving your understanding of what happened after you implemented treatments, and how you can use that information to adjust management and adapt to this high level of variability out on rangelands. Rangelands are pretty much characterized as dry. That's just one of their defining characteristics, but their other characteristic relative to weather is that rangelands have highly variable weather, particularly in the west where there's such complex terrain. You can have very high variability in weather inputs just over a very short space. This is the weather record for Boise, Idaho, which is on rangeland in the Intermountain West. Those red bars are average annual precipitation. Average precip in Boise is about 300 millimeters. You can see how variable it is from year to year. Those blue bars are spring precipitation variability. In March, April, and May, about a third of the precipitation falls in Boise. That's a critical period for plant establishment before things dry out. And you can see that if anything, it's more variable during the spring than you see annually. Weather data can fool you. On the left here in the green box are 4 years that are better than average annual precipitation. Every one of those years was lower than average, maybe even half average or 60% of average for spring precipitation. So you have to be aware of the time period you're interested in or investigating if you're trying to interpret weather effects. That green box on the right shows 2 extremely good years and for annual precipitation, and one has over twice the spring precipitation and the other one is less than average. So this is even exacerbated if you look at a smaller temperature or time interval. This is the same period of record for May precipitation. The shorter the time interval, the more highly variable it is. We sometimes measure variability with the coefficient of variation, which is the relationship between an estimate of variability and the mean. Spring precipitation is twice as variable using that index as annual variation, and any given month is twice as variable as the spring. May is twice as variable as March, April, May in total amount of precipitation. You can see in May, boy, if it was, I guess that's 1974 or 89 or 92 or 2002, it probably didn't matter what you did. May would kill off your seedlings. This is extremely important now because we're finding that a major bottleneck to establishment success is the phase between germination and emergence. After the seeds germinate, if they don't have sufficient resources or it's too cold to elongate a root and start growing vigorously, they're highly vulnerable to relatively short-term mortality events through freezing or relatively short-term drought. We're finding more and more that we can use some of these weather indices to characterize the favorability of microclimate, but it's also important to understand these episodic events that can kill seeds at important stages of their life cycle. I'm going to talk about adaptive management. It's another topic that the EBIPM program has produced a guidebook for. I'm going to use their guidebook to structure my presentation, and I'm going to use their diagram for adaptive management and talk about weather and climate use and planning in the context of this diagram. The first things you do when you're planning rangeland restoration is you set your goals. One important thing is if you're interested in incorporating weather information, find some weather collaborators. Historically, the Weather Service and people providing weather information have had historical clients, the Department of Defense, the FAA, the nightly weather forecast. It's only fairly recently that the people that are involved in collecting weather information have refocused on a lot of the more management activities, particularly in the West. Agricultural applications for weather information developed more quickly. We don't use it as much in the West, probably because we have such complex terrain and such low densities of weather information that it's just been slower to develop. But if you can find weather collaborators, we'd like to be your weather collaborator, but finding people who can help you will get you pretty far down the road. The other thing to think about at the goal setting stage is longer term goals. A lot of our restoration activities are one-year activities. Maybe they're instituted right after a fire. a plan is developed within 2 weeks of the fire, it's implemented that year, and then we effectively walk away. Another implication of this variability is you might have to expect multiple intervention with these longer-term goals. Usually, a lot of times you do have complete failure. Most of the time you have partial success, and partial success might mean 1 or 2 species establishing for a while that need to be sustained but that don't meet your long-term goals, and you maybe need to think about additional activities over a longer time period to achieve those goals. Second step in this adaptive management plan is the step for collecting information. There are a huge number of sources of weather information. This is actually a problem because all of these sources are relatively uncoordinated, and in the West in particular there's such a low density of weather stations that it can get confusing where you get your information. It might be in a different format, it might be for a different period, but there is a lot of information out there. This current slide is a graph of distribution of what we might call Class 1 NOAA weather stations. It's the kind of thing you have near the airport or in major cities that has very detailed hourly information. You can see they're pretty sparse. If you back up a little, you can almost define the Intermountain West as the area with the lowest density of weather infrastructure. It's a much higher density of lower resolution data. This is often all we really need. This is a picture of the NOAA co-op network. It's a bunch of volunteers that go out once a day and monitor total daily precipitation and minimum maximum temperature. But it's done all over the place, and there's a lot more of this data because it's a bunch of volunteers. Sometimes the data quality is lower, but this is another source from the same group that produced the Class 1 weather data. If you want to download this data, though, you have to go to 2 different pages. It comes out in a slightly different format. Most states have some kind of statewide network that has been put together in support of that state, mostly the state's agricultural community. This is an example from the Pacific Northwest. The Bureau of Reclamation has an agromet network in support of mostly traditional row crop agricultural applications, but if you look down there in southern Idaho, those ring the Snake River Plain, which is an important area of rangeland in southern Idaho. Agromet's only been around for 20 years, so you might have a different period of record. It has different format, but if you're looking for data and there's a weather station near you, it doesn't much matter where it came from. There's some other relatively more obscure data sets. People familiar with this data wouldn't call it obscure, but BLM operates a ROS network of weather stations primarily in support of fire weather applications. The disadvantage of these data are they usually aren't year-round. Some of them have extremely short periods of record. The advantage is these are out in the middle of nowhere frequently, and if you need weather data out in the middle of nowhere, sometimes this is the only place. There are groups that are creating value-added products and consolidating weather information. One of the most useful to us in the West is the Western Regional Climate Center. They have a number of applications and data sets and synthesized information that's very useful, and that's often a place you would go to get information that you can't get anywhere else. One of the first things you need to do when you have weather information is to download it and plot some averages just to get a sense of how your particular site varies over the year in terms of these principal weather inputs of precipitation and temperature. Again, this is an example from the Boise weather record. Temperature is always a lot more consistent from year to year than precipitation, but you can get a sense of when resources are available and when you have problem areas, so that when you're looking at year-to-year variability, you have a context. Often the important things are going on at different times of the year. In Boise in the late fall, you can have significant weed emergence and growth. Those weeds can extend their roots through the winter when the things that you may be planted at the same time in the fall are just sitting there. Maybe they germinate but don't emerge. How much precipitation you get in the winter is tremendously important, not so much during the winter, but during the summer in terms of soil moisture storage and survival. If you have the flexibility to adjust your plan to take advantage of seasonal information, you could perhaps do things in the spring based on your understanding of how good a winter you had. Typically in the spring is when things are really happening though for initial establishment in this area, and as you can see that's where the precip starts dropping and the temperature starts going up. April, May, June, those are critical months for establishment of seedlings in the Boise area, and then whether or not they get through the summer might be dependent upon how much moisture was stored in the winter. One of the things that we're proposing in our EVIPM guidebook is that you put your restoration plan in the context of the historical variability of your site. If you have long-term weather data, you can rank that data and see what kind of variability you get. This is just a ranking of the Boise data based on annual precipitation. One thing you can note is even though you ranked it by annual, that spring precipitation is still highly variable. Maybe you want to rank it by spring precipitation to get a better idea of what's going on. I may have mentioned before we did a synthesis of the rangeland planting literature a couple of years ago, and almost all of the papers that were published on rangeland planting that mentioned weather noted that the year of the study was either average or above average. That implies that there probably are thresholds, and managers know there are thresholds for successful establishment. The literature would suggest that unless you're average or above average, you don't get success because publications come out when they have results, and in bad years you have no publishable results. That's something to keep in mind when you're planning, that you're going to have years with low success and lack of success. These are things we know, but this is a way to put that in perspective and quantify expected variability. Or if you have information on past plantings or you have a lot of experience with plantings, this is a way to look at particular years and see what the weather impact might have been on the success of your management in previous years. In developing a plan, this weather variability lends itself to ideas about planning for partial success, not just non-success. It's probably more typical that if you have a rangeland planting, something was successful. It might not persist in the long term if the weeds are allowed to return, but typically out in the areas I'm more familiar with, say out in the Snake River Plain, you might have partial success. Maybe all of the sagebrush that you planted came up and everything else that came up in the understory was an annual weed. That poses a real problem because if you want to go back in there, you don't want to rip out all the shrubs that you want to maintain out in, say, birds of prey area, but you want to deal with the cheatgrass and get some more desirable plants in the understory. This is a little more complicated scenario, but the partial success is probably going to be the predominant result of any given year's activity. It's always important to evaluate what you did and establish controls so that you can see what would have happened if you didn't do anything. These controls really have to be long-term controls, and if you have the flexibility to repeat your treatments over time, even if not at a large scale, that's the only way you're really going to be able to tell whether specific treatments are more favorable in general, or if you have some new idea, whether that's a really good idea or a bad idea, because weather variability is such an important driver of success that you really have to put your success or failure in a given year in perspective, and that requires long-term monitoring. It's also important to replicate across years if you are trying out a new treatment. 1 or 2 years is generally going to be insufficient to survey the variability you would expect at a given site. The Adaptive Management Guide talks about meeting to agree upon a plan and adjusting a plan. This is the part where you get involved with stakeholders. This is the predominant thing that happens if you're on federal lands and you're planning restoration projects. You have to put together scoping documents to solicit stakeholder input before you even start an environmental assessment. You put your plan together, you have to meet with stakeholders again. Because of this variability, it's important to discuss what success means in this variable environment with your stakeholders. If we're doing restoration in the Boise front, just up above Boise in the foothills, it's under the scrutiny of a lot of people who don't have any familiarity with rangeland restoration techniques. All they see is someone out there spraying weeds or disturbing the soil. They might not recognize that the dominant plant community is invasive annual weeds. It's very important to explain, number one, how what you're doing relates to this dynamic system and is a long-term project. Sometimes your stakeholders might be your boss who is expecting something from a management that results from an EA you're writing or a plan that you put together right after a fire. When you're putting together these plans, you have to consider these long-term, multi-year adaptive management in a more formal setting in your planning documents. If you're writing an EA, a lot of restoration EAs are principally, this is what I want to do on this site. You get permission and you do it, and there's really no ability to respond to contingencies. Department of Interior has put out guidance on adaptive management and things like contingency planning, and one of our collaborators right now is the Bureau of Land Management out at the Birds of Prey National Conservation Area. We're putting together EAs that take into account the fact that we can't predict what's going to happen in that first year, but we have contingencies for various alternative management outcomes in that first year. That will allow us to respond to what the weather allows us to achieve in the first year and then go in the second and subsequent years with adaptive responses that can take advantage particularly of partial success. A lot of our funding for rangeland restoration is in the context of emergency fire rehabilitation, where a place burns, you have 2 weeks to come up with a plan, and then that money gets spent mostly in that year. We're doing a couple things to ameliorate that situation. One, as we're talking about developing proactive fire rehabilitation plans, there's no reason you can't put together a fire rehab plan before an area burns, particularly if you know eventually it's going to burn, and have the leisure to incorporate some of these ideas of weather variability and adaptive management in your fire rehab plan. Just do it ahead of time. We're also writing EAs that pretty much leverage the fire rehab plan. If you have a fire and there's a fire rehab plan, that's a good time to write an EA for adaptive management for follow-up after that first year's intervention. If you have a restoration plan, particularly if it's a large area where millions of dollars are going to be spent, it's worth considering putting your own weather collection instrumentation out on that fire so that when you try different things or have different levels of success, you have some weather information for interpretation. Another thing that's important, we talked about some of these bottlenecks for seedling establishment. The process of establishment of plants is a cycle that has many phases, each of which is affected by particular weather and climate conditions during that phase. A lot of times when we do monitoring, it might be only in the year after seeding, might be only plant density or biomass. A lot of times the critical factor for successful establishment is what happened between germination and emergence, or what might have happened to juvenile seedlings during the summer. It's worth considering monitoring more frequently so that you can tease out exactly what went wrong or what went right in a given year. Once you do have information, particularly if you do this a lot and you have a lot of historical information, is to go ahead and look at your success and failure and partial success and go ahead and plot it as a continuous variable, looking at those ranked precipitation years in particular to put your success in context. When you're evaluating your success, it's important to put it in perspective. This is that diagram from before of what might be possible in different years. If it's a good year, a lot of things might be possible. If it's a bad year, you might be locked into this cycle, and it's important to interpret your success and failure relative to what the weather did. So some of the main ideas for planning and adaptive management given high weather variability is to consider longer-term goals, at least expect some failure or partial success, and think about how you would react to those under different weather scenarios. It's important to interpret success and failure by using weather indices. It's important to monitor effectively given weather variability, which means longer-term monitoring and replication and maybe repetition of treatments in future years at least a small scale so you can get a better idea of how your management affected success. Another really important thing is to be, if this is useful to you, is become an advocate for weather-based planning, management, and logistics. Full use of weather information may require us to adjust our management scenario, and it's always difficult to change the momentum of planning scenarios. I wanted to mention a couple things that are on the management horizon. These are mostly things that I'm involved with collaborators that I wanted to talk about. And because this is a GBRMP sponsored webinar that is supposed to talk about collaborative opportunities, I want to invite you to think about how you might use this information or interact with us, or maybe use some of the resources we're creating for your own purpose that is unknown to us but that might be clear to you. We have an AFRI grant this year to look at forecasting applications, global climate models that are used to predict climate change 50, 100 years out can also be used for seasonal forecasts. That's very appealing for rangeland restoration, especially when you have to make planting decisions in October, November. It would be very useful to be able to have a prediction of, say, spring favorability of microclimate. This AFRI grant we have, some of my collaborators are John Aboxoglu at the University of Idaho, Matt Germino at USGS, and Mark Brunson at Utah State. How would you use forecast information? Say your area burned and you wanted to use forecasting information in a burn rehab scenario. You might not have an option, you have to do something, but you might ask yourself, do you want to use a weed control procedure if you know it's going to be a very bad year? We have things that will kill weeds dead, and if the weather doesn't allow you to establish what you want, you might end up with bare ground that's highly erosive. It might be better off not to control weeds. If you're making decisions about buying expensive native plants, maybe you would make different decisions in a bad forecast year. Maybe if you think it's going to be a bad year, you'd focus on soil stabilization, plant something that's more likely to be established, and deal with native plant diversity in a future year when you have a better chance at getting natives established. If it's a non-fire year, maybe you have more flexibility. You might just decide if it's going to be a bad year, you're not going to do anything. Or if it's a good year, you focus your resources and try to take advantage. You might ask whether you control weeds and plant natives, or maybe you would control weeds and plant non-natives, or if you have planted non-natives, this might be the year you want to control the non-natives and plant natives for native plant biodiversity. objectives. Right now, seasonal forecasts are pretty crude. The Climate Prediction Center creates these maps for different periods in the future every month that give probabilities of exceeding a particular average condition from history. These models were initiated to ask questions like, are we having climate change on the Earth? They weren't really optimized for our discrete applications. The Climate Prediction Center actually uses 8 or 10 or 12 different climate models that they pool for these predictions. One of the objectives in our AFRI grant that John Aboxglou is working on is to look at these individually using hindcasting with historical weather data, because some of these models will work better in different areas during different weather scenarios, perhaps during different periods of the year. And there might be one model or two models that work much better for, say, rangeland restoration applications in southern Idaho if you're planting in the fall and you want to know what's happening in the spring. That's something we're going to determine. We're considering rangeland restoration applications. I can think of a number of other applications that could use the same tool. If you have something along those lines, you should contact us. We're also working with several groups with sponsorship from EBIPM, AFRI, the Fire Science Delivery Project, and collaborating with USGS, the USGS Powell Center, Oak Ridge National Laboratory, and the DAMET Group and the Western Regional Climate Center to improve availability of actual weather data for people like us who need them for rangeland restoration applications. One thing we're doing is creating something of a one-stop shopping for weather data so that you can just go to a site and see what's around you regardless of source and download it in the same format. We're also working with Oak Ridge National Laboratory and John Aboxglou on a couple of gridded data sets. There often isn't anything near where you need weather data. The DAMET data set is a 1 kilometer grid of weather variables. John has developed a 4 kilometer grid of a bunch of relevant weather variables. We're also going to include that in the one-stop shopping for weather data if you want to develop a historical scenario for your location. We're also looking at topographic effects. If you look at plant distribution at a smaller scale, you see southern exposures and northern exposures, and ridge tops all have different vegetation. If it's the same general weather input, that's often because the solar radiation differs, and we're doing modeling and trying to incorporate topographic effects into our weather products. One project we're doing with USGS Land Treatment Digital Library is to retrospectively assess BLM seedings. We're going to go back and pull out seeding data that's good enough to evaluate and overlay weather indices to see what kind of weather thresholds might exist for different management activities and seeding mixes. We're working with NRCS to develop weather and microclimatic supplements to ecological site descriptions. This is usually the first place you go if you're in an unknown area and you want some information on the site for restoration. You go to get the ESD, you look at the soil type, you look at the state and transition model to see what appropriate plant materials might be suitable for this site. ESD information currently includes gross weather information, but we want you to be able to click on a latitude or enter a latitude and longitude, select the soil types that you may be interested in, and come up with more of a microclimatic scenario for those sites than just weather. When you look at weather impacts on seedbed favorability, it really only explains about half of the favorability, and you have to take into account all these other microclimatic features to come up with a better estimate of what the seed and seedling actually sees. I can think of a number of other opportunistic applications. We're working with some people using distributed hydrologic and water and erosion models who need similar distributed weather information and similar access. We're working with people looking at species distribution models, particularly of cheatgrass, and we're trying to link our mechanistic microclimatic models with existing climatic distributions of things like cheatgrass. There's a lot of interest out there in monitoring. There's actually a national network of people who monitor phenology across the United States. Phenology is frequently related to thermal time and hydrothermal time and weather and climate index concepts. We're open to any kind of collaboration. This webinar is part of a series sponsored by GBRMP and the Joint Fire Science Delivery Project. We created GBRMP to facilitate collaboration. If there's anything you see in this presentation that you think could be a benefit to you along the lines of restoration applications or any other application, please bring it up and we'd be happy to work with you. I wanted to just put up a slide with all these collaborators. A lot of the stuff I described has almost nothing to do with what I'm personally doing and relies on working with all these other people. I just wanted to thank and then open it up for questions.
Thank you so much, Stuart. I'm really sorry. When I was trying to unmute myself, I actually muted Stuart for a second, but I think we got the gist of it. Okay, so if you have questions, please type them in to your questions pane. And I'll start with the first one. Kristen Williams asked, this is actually more of a question for me, will you be sending out the PowerPoint and or useful links that were mentioned in the presentation? And yes, we are going to post the webinar and a PDF of the PowerPoint on our website, and I will try to get that done by the end of this month. But I'm sure if you email myself or Stuart personally, we could send you the PDF sooner. Okay. Any more questions? I'm waiting for them to arrive in the text box.
Well, while we're waiting, I can just mention that a lot of we're developing a lot of tools that we're going to be posting on the Joint Fire Science site and the EBIPM website, guidance and spreadsheets and access to these data. What we envision for a lot of this is you'll be able to type in your latitude and longitude and download a suite of information based on what you would like to see, weather and climatic summaries from these gridded data sets, comparison of gridded data with local weather data, microclimatic simulations that are run on the fly so that we don't have to model every square meter out there, but that allow you to select from different options and come up with these microclimatic scenarios for your particular location.
And Stuart, will that be on the www.ebipm.org website?
That will be one of them. We have several places that would host this information, including our NWRC website with ARS.
Okay.
A lot of times they'll be posted multiple places as links and maybe only be on one server, but they should be out and about, and we'll advertise them through things like GBRMP and the Science Delivery Project.
Sounds great. Okay, next question. Retta Bruger asks, where is the manual you mentioned on adaptive management of cheatgrass available?
All of those manuals that I showed in the one slide and others are available from the EBIPM website. It's pretty easy to just Google EBIPM and it usually comes up as the top. It's easy to Google GBRMP too. The only competition is some barrier reef site, but you can pick up GBRMP in there. All those manuals are available for download, and there's probably someone you you can probably, there's a contact on the EBIPM website if you prefer a hard copy.
Great, thanks. The next question is from Susan Fritz. What are some examples of adaptive response if first year is not as successful as you thought it should be?
Well, this is where we're entering new territory. Most plans really aren't long-term plans. Most monitoring isn't really long-term monitoring. What we're envisioning, we're developing an EA for a high priority area out at the Birds of Prey National Conservation Area. What we're going to have to do is come up with a matrix of potential contingencies, mostly based on what we may have seen in the past. I've been on a lot of tours out at Birds of Prey historically where you actually see a lot of successful establishment, but without additional weed control, the weeds move back in. Maybe there's another fire. So I think one really good example would be protecting what you establish. Some of the, particularly the chemical treatments we might use to control annual weeds have a relatively limited lifespan, and they might knock the weeds back, but they'll return sooner or later. So that might be one example, going back in with an herbicide like Plateau, which is relatively selective for annual weeds, and knocking them back in a future year. The other thing would be, how do you plant? And you might have to get creative. There are a lot of places out there that do have sufficient cover of things like sandberg bluegrass, or maybe have sufficient shrub cover. The question becomes, can you use low-till drilling or some other procedure to not disturb what you got established?
Thanks. All right, Cynthia Brown asks, what are the geographic limits of the weather data that are being used for different applications? All of the U.S., West only, etc.?
Well, I started as small potatoes, and I was just thinking, well, I'm part of the Great Basin Research and Management Partnership, all limited to Great Basin. You talk to any weather person, they have no such limitations, and they don't want to consider anything pretty much less than the contiguous U.S. So all these weather data and gridded data sets are for the lower 48 states. When talking to NRCS about ESD applications, which is principally a Western application, there is an equivalent pasture concept and for the Eastern U.S., so they aren't interested in limiting it either. So right now we're talking about the 48 contiguous states.
Thanks. Ryan Shane asks, I like the one-stop shop. It will be very helpful. The crux is still the predictive power for the following spring. Will these outputs also include the predictive probabilities for each latitude and longitude?
That's what we're focusing on with this AFRI grant. John Aboxaglu's objective under that grant is to use 30 years of this consolidated weather data to effectively, for each of those years, create a forecast and test these individual predictive models to see which ones work better for our particular application. I'm not sure what the limitations are in terms of applications, but one for sure will be this fall application for predicting spring weather. We'll have evaluated these models, and once we determine which models are best for which applications, we'll include that in a web interface so that people can extract this information when they need it for planning. The Weather Service does this with the Climate Prediction Center, but as I mentioned, those models are pretty coarse for our applications. But the people working on this say that if you have a specific location and you have a specific application and a specific time period, you can use individual models that give you much better predictive capability. One of the objectives of this AFRI grant is to make all this information accessible, and we're also incorporating manager input. Mark Brunson at Utah State is focusing on this to make sure that what we put up on the web is valued and at least partially based on what managers say they can and will use.
Great, thanks. All right, David Pike asks, have you looked at how correlated the regional climate forecasts are relative to that year's weather? It might give managers an idea of how useful this approach would be.
That's the principal objective of our forecasting with this AFRI grant, is to test that. I'm hoping that we can maybe expand our vision beyond the rangeland restoration applications, because there's really no reason we can't test these models. The computer will be doing a certain amount of the number crunching for pretty much any place we have weather data, and for any time period you want to forecast from, and for any length you want to forecast to. But yeah, that's a principal objective. We have to test the utility of this approach before we can tell how useful it will be.
Great. Okay, well, that is the last question. I want to let everyone know that a recording of this webinar will be sent to you automatically through the GoToWebinar system tomorrow, and I will also post it on the Great Basin Fire Science Delivery website, where it will be housed more permanently, and I'll try to get that done by the end of the month. If you have any more questions regarding this webinar or other topics, or have requests for future webinars, please email or call me at any time. And I want to thank you all for your participation today, and thank you so much, Stuart, for your presentation.
You're welcome.
All right, well, have a great day, everyone.
Thank you.
Thanks.